So hello everyone. So this is Hao Jiexu from Huzhou University. So I'm very glad to give a talk here. And the title of my talk is the neutron skin determinations via isobar collisions. So this is the outline of my talk. So first I will discuss the nuclear structure of isobars. And then I will focus on how to probe the neutron skin thickness and also the nuclear symmetry energy using isobar collisions. And then it's a summary. So let's go to the first part of my talk, the nuclear structure of isobars. So as the goal of this program, we're trying to make a connection between the nuclear structure and the relatively heavy ion observables of the final state. So this is the time evolution of heavy ion collisions. We collide the two nucleus at high energy. We create a hot and dense medium with deconformed quark and gluons, which is a quark-gluon plasma. After expansion and freeze out, we got to the final observables. So actually, there is one very well-known connection between the initial spatial anisotropy and the final isotropic of momental distribution, which is called isentropic flow. So usually people use these properties to study the bulk connections to study the bulk properties of the QGP mediums, like the shear viscosity, the bulk viscosity, and so on. So in the main goal of this program and also my talk is trying to extract or study the nuclear structure. So basically people use the Wood-Saxon distribution to describe the nuclear densities like this, and they have some parameters like the diffusionist parameters, the radius parameters, and also deformation parameters like beta 2, beta 4, and so on. So in this talk, I will discuss the isobar collisions, and you hear a lot about the isobar in this week. And the isobar was proposed to measure the carrier magnetic effect, and Fu Qiang have a very nice talk on that. And also in the previous speaker, Guo Liang gave a very nice introduction of the carrier magnetic effect. So in short, in isobar collisions, people expect that the zirconium collision and the ruthenium collision will have the same background related to the geometry, because they have the same mass number, so people expect they have the same collision geometry at the same centrality. But the ruthenium have 4 more protons than the zirconium, so it will create a large magnetic field in ruthenium collisions, so they will have a larger CME signals. So if we look at the ratios between the of the CME observables between ruthenium collisions and the zirconium collisions, people original expectation is that this ratio should be larger than 1 if we have some contributions from CME. But as you know, last year, Star have published the first result of the isobar, the CME measurement in isobar collisions. You will see that all the ratios are below than 1, and below to 1 means that the background are not identical. We know the background are not identical because the zirconium are not ruthenium. They have some structural differences. But in previous study, people trying to use the charge densities to see the isobar differences related to the CME measurement. So they use the Wood-Saxon parameters extract from the charge density distributions, and the parameters are listed in this table, and they calculate the multiplicity distribution ratio on the left, and also the eccentricity ratio on the right, which is related to the elliptic flow ratio. And these two are main contributions for the CME background shown in this formula. So if we focus on the long central collisions, which here in the middle multiplicity range, you will see that the multiplicity distribution and also the eccentricity are almost similar for the two systems. So this is a good news for the CME search in isobar. But you know, as I shown in the previous slide, the star data tell us that the background are not identical, and we trying to ask why they have some differences and what is missing in their studies. Actually, before the isobar runs, we also already realized that the charge density cannot be used in the isobar simulations. And the answer for the previous slide is of question of previous slide is that the charge density is the not nuclear density, and this is obviously, but normally in relativistic heavy ion collisions, we always use normally use the charge density instead of nuclear density for our simulations. One of the reasons is that we know that the charge density can be measured precisely in nuclear experiments. So we typically use the charge density as input in hydro or some heavy ion relatives heavy ion simulations. But in our isobar simulations, I will show you that these differences cannot be neglected. Since the mass density or nuclear density cannot be very easy to measure, but we do have some fundamental theory to calculate it. So in our study in 2017, we used the energy density functional theory to calculate the proton and the neutron densities of ruthenium and zirconium. And in this plot, we shown make a comparison between the DFT calculated nuclear density and the Anglo-Saxon parameters, the charge density. They do have some differences, and most importantly, we are showing you to use that they have some very different prediction on the CME related background. And in here, I shown the predictions with different set of nuclear density. On the left panel, I shown the predictions with charge density. And on the right panel, I shown the predictions with the DFT calculated nuclear densities. So if we look, focus on the top panel, this is the multiplicity distribution ratio. You will see that the multiplicity distribution ratio prediction with charge density have low differences at the middle central centrality, but at most central centrality, the ratio is below than 1. But for the DFT calculated density, the prediction is that we see a very obvious non-trivial bump structure at the middle central collisions. And for the most central collisions, the ratio is above 1, not below than 1. And also, if we focus on the lower panel, this is the eccentricity differences between the two systems. On the left is the prediction with the charge density. You can see that at non-central collisions, the ratios are more close to 0. The relative differences are more close to 0. And they have differences, and most central collisions are mainly due to the nuclear deformation. And in our DFT calculated nuclear density, we predict that the eccentricity ratio or the V2 ratio have a non-trivial bump structure at the non-central collisions, and the differences could be as large as 3% here. And we have the star data, and the data and with the data comparison, we found that the TFT the DFT predictions are verified by the star data. On the left plot, I show the multiplicity distribution ratios, and we can see a very clear bump structure here, and can be described by the DFT by the calculations with DFT calculated the nuclear densities here, and also the V2 ratios at the non-central collisions have a long trivial bump structure. And if we focus on the multiplicity distribution ratio at most central collision or a high multiplicity range, you will see the ratio is above than 1, not below than 1 predicted by the charge density. So let me first explain why they have differences on the predictions with different set of nuclear parameters. So if we talk about the nuclear charge density distribution or the proton density distribution, actually it can be well measured by the low energy nuclear experiment. And the experiment is the measurement tell us that the ruthenium have a larger charge size than zirconium. But if we talk about the nuclear density or the mass density, we should include the differences between the neutron distribution and the proton distribution, and it can be characterized by the neutron skin thickness. It's defined like this: is the IMS differences between the neutron the distribution and the proton distribution. And the DFT tells us that the zirconium have a larger neutron skin than ruthenium. So if we consider the neutron distribution and the proton distribution differences, and we see that the mass size for ruthenium is smaller than zirconium. And in heavy ion collisions, if the two systems have the same total entropy or energy, the smaller overlap range or smaller size indicate a larger density. They will create a larger multiplicity and also mean PT. So that's why with the prediction of the DFT calculates the nuclear density, we have the ratio of ruthenium over zirconium for the multiplicity distribution is above 1. But if we use the charge density, the ratio is below than 1. So let's also explain the next differences of the predictions, why the DFT calculated nuclear density shown a very obvious non-trivial bomb structure for both the multiplicity distribution ratio and also the V2 ratios. So we know in the Wood-Saxon preparation framework, we have two ways to introduce the neutron skin. One is the skin type, another is the hero type. For the skin type, we see that the proton density and the neutron density have the same diffusionist parameters A, but the radial parameters R are different. But for the hero type nuclear, we see that the proton density and the neutron density have different diffusionist parameters, but the reduced parameters R is the same. So in this study, we construct two different neutron skins for the zirconium. One is the skin type and another is hero type. And then we calculate the multiplicity distribution ratio shown in the middle panel and the eccentricity ratio shown in the right panel. You will see that only the hero type nuclear can predict a long trivial bump structure at long central collisions. So the shape of the ruthenium over zirconium ratios of the multiplicity and eccentricity in middle central collisions can distinguish between the skin type and hero type nuclear densities. So there's also another interesting thing that about the charge density is not the nuclear density. So if we look at the cross-section of the photon production of dilepton, you will see the cross-section is only related to the charge densities. But when we make some baseline prediction of the photon production dielectron cross-section in our study, we will focus on some centrinity, for example, for the 40 to 80% centrinity. Although the cross-section is not related to mass density, but the centrinity definition do depend on the mass density. So we found that if we use the charge density to define centrinity, we will give very different prediction of the ratio of dielectron cross-section between ruthenium and zirconium. So now we know the neutron skin or the nuclear structure can affect the final observable in isobar collisions. So the natural question is, can we use these final observables to determine the nuclear structure of the isobars? So this is the.
Can you go back to the next slide?
Okay.
Okay. So why is that different? Also, the PT dependent shape, is it reason? I mean, simple way to understand that.
So we use the same charge density. The cross-section is only related to the charge density. So the calculation of the cross-section is the same for the two cases, but the centrinity definition is different. For the left panel, we use the DFT calculate the nuclear density to calculate the centrinity for both ruthenium and zirconium. And on the right panel, we use the charge density, only use the charge density to give a prediction of the ratio.
What the PT dependence coming from what? There's some ratio, there's a different PT dependent shape. On the left is like overall like offset of 10%, the other is like no.
This is coming from the different, which means if you in other words, the multiplicity range are different between the two systems, and the multiplicity, the PT distribution is dependent on the multiplicity. So that's why they have different behavior of the ratio.
It's the centrinity definition, basically.
Yes, the difference from the centrinity definition. And the PT distribution is dependent on the multiplicity, also the centrality, or in other words, centrality.
I have a question about the previous discussion. So where you sort of conclude about the halo.
Yeah.
I mean, there are indeed differences in the diffuseness between protons
Yes.
and neutrons, but by no means as big as to account for the skin. So why do you think this is good? I mean, this is sort of, I don't think there's any evidence on structure side for the skin being due to the diffuseness.
I'm not sure I'm understanding your question.
I mean, you have here three cases. Neutron,
Yes.
neutron skin by the shifting of the radii, and then skin by changing the diffuseness.
No, the halo changed by the diffuseness.
Whatever you call it, halo.
Yes.
The skin is not due to halo.
Skin is, we can vary the diffuseness of the
I
radio.
hope that you can vary and you get this result, but I mean, it doesn't bring a confirmation of anything from structure. It's just an excursion in still another direction.
It appears that
Yeah.
the structure that you calculate can be captured by A naught in this particular quantity.
I know, but it is not, because it's inconsistent with what you know from structure.
What we know from structure?
We know from structure, you know, that there's basically a change in R, there's some change in A, but it's not big.
So what's the percentage contribution?
I can look or something, but it's basically a change in R.
It's so what I think what Hodge did here is that he took the calculation.
I know, I understand. what
Prompter
you did.
states.
I know, but I mean. Anyway, yeah, I just go ahead. I mean, this is just a comment. Just go ahead and talk.
So let's explain a little bit. Since we use the same F for proton because the proton distribution can be measured precisely in experiments. So then we can construct
Right, but I mean, it's not that you don't know nothing about nuclei and you can change anything and it will be valid.
Yeah, this is the two extreme cases to change it to give the neutron skin. So I mean the data favor a skin type, a halo type, not means that this is exact a halo type. They have some difference in A.
Then I can say it's a puzzling result.
Hojia, this cartoon, where you get this cartoon? It's from some theory from nuclear structure, right? Oh.
Yeah, yes. They
I
just
think
in
you can see the
very
reference. We may take a look.
very simple illustration of which one is the skin type, which one is halo type. Yes.
It's very unlikely that these nuclei have a halo.
For halo, we have a large tail distribution.
They are in the value of the stability, so I don't think this is a halo.
But it appears that if you keep the A naught to be the same, then you cannot explain the data. So the A naught have to be different.
Then you have to look for something else.
Okay, but A naught is different. Probably they both in order for proton and neutron, they are all small. It's not like only the neutron. So they both have become sharper.
I think A is this, presumably A for neutrons is a bit smaller than proton.
They're actually small. Okay, could be. Okay, so that could be a fact.
Right, but it's the other direction than the data suggests.
No. His data doesn't constrain proton and neutron separately. What matters
No,
always the
it's
size.
relative. So if he puts a short.
Larger A naught for the function, yes. For the neutron,
Yes.
A naught. Appears to explain data. His values, right, the RA will obtain from the DFT densities. Just do a Wood section factorization of the density.
Right, but so the halo type came from DFT?
Yes, I believe so.
So how come you can change the the two types of skins in TFT? How do you get it?
What?
I mean, if it's DFT shouldn't give such results.
Sorry, in this slide,
Cannot give you two results.
in this slide, we didn't use the DFT calculated nuclear densities. We just make a example test. So for the neutron halotype, skin halotype. For the DFT calculations, we use the first and second momentum of R to extract R and A, and also this extraction indicates that the DFT calculated nuclear density is also halotype. Yeah.
DFT also gives you density, right? That you don't need to fit with anything.
Yeah.
Yes. Yeah.
There's no physics that would give a halo or within DFT for this nuclei.
I missed a link here. So you can use the density from calculation and do all these calculation, and that's what Hodge got as well. That's
Yes.
And I thought, Hodge, that you took the density, the calculated density, and use water section formula to fit that to get those parameters.
Well, he just fitted the moment.
Yeah. We already do that, but not shown in this slide.
Yeah. Fit the moments.
But moments you have two parameters and just one moment, right? So you can trade it this way or that way.
We use the first moment and the IMS, the second moment, to extract R and A.
So is the plot A, is that the actual result of the fitted values? Is on the left, plot A, is that the actual neutron distribution?
This is just an illustration of how to extract, construct a neutron skin and see the effect for the relaxed heavy ion absorbers. It's not related to real densities.
Your numbers are from the calculation or not?
No, that's just for illustration, not from calculations.
Oh, okay.
We also do the calculations, but from the DFT calculated densities, but not shown in this slide.
Oh, okay.
But the results are similar. The DFT calculation, if we use the Wood-Saxon factorization to get the R and A, we also see they have small differences in R, but not differences in the
ratio.
and the prediction are similar to the halotype.
You only get 3% for the halo, right?
What do you get when you take directly the DFT densities without Wood-Saxon parameterizing them and then take the ratio of these observers?
This is my precision ratio from the DFT calculated nuclear density and compared to the star data here.
So this is without Wood-Saxon feeding.
Yeah. This is from the real nuclear density, and from the nuclear density from this slide are not just the illustration the difference between the skin and halotype nuclear. So this is not really.
But so then maybe in another direction. So are you claiming that you can tell the difference in density distribution from DFT and Wood-Saxon?
I cannot. If we use the first and second momentum to extract R and we will give the similar prediction on the at least for the multiplicity distribution ratio and concentration ratio, they are similar. So we cannot distinguish two cases. Yeah.
I was initially puzzled about that.
Okay.
I thought you would see some differences.
Yeah, but if you could, I mean, it's very important, right?
Yeah.
Okay, please continue.
Yeah,
So
sorry.
for the picture A, why the skin type and the halotype, they are the difference between neutron spin are same already. Somehow the halotype could be larger.
Sorry.
I mean the skin type, the difference is equals to according to 0.123. halotype still 0.124 Fermi.
That's an imposed constraint that he imposes. This is not calculated, this is imposed.
Oh, okay.
I think it's the difference between red and blue in the bottom part.
Oh,
It's they're different, but and one side one way and the other side another way.
Okay, so let's move to the second part of my talk. Then I will focus on how to probe the neutron skin thickness and the nuclear signature energy using the isobar data. So, as I said, the zirconium have a larger neutron skin than ruthenium. This is because the neutron skin are simply related to the neutron proton asymmetry, and the zirconium have a larger neutron proton asymmetry shown here. But more seriously, we can use some fundamental nuclear structure theory to calculate it. So we use the density functional theory and with the Skymon-Hatch-Fokker model. And this is related to the symmetry energy, and one of the most important parameters is the slope parameters of the symmetry energy is defined here. And we can compute the L value at the saturation density, ρ0, and also the subsaturation density, ρc. And if we have a larger L value, then we have a harder equation of state, which we need means we need a smaller delta to noise energy. So we have a smaller neutron density. So we have a larger neutron skin. Actually, people found that the neutron skin and the L parameters have very good linear relations shown in this slide, in this plot. So the symmetry energy, as you know, is crucial to our understanding of the masses and the drop lines of neutron and rich nuclei and the equation of states of nuclear and neutron star matter. So we know currently the PEREX-2 collaboration have published their measurement of the neutron skin of the benchmark nuclear lead. They gave a larger neutron skin thickness and a larger L parameters compared to the worldwide data. And this is at attention with the existing experimental data and zero analysis. And if our relativistic heavy inclusions can give some information of the L parameters, and it would be useful. So to make a connection between the neutron skin or nuclear symmetry energy to our heavy ion observables, we calculated the nuclear density for ruthenium and zirconium at different L values. And the model we used is the standard SHF model and also extended the SHF model, which means we effectively include the three-body potentials. And this table shows the L values at different, the LC value with different value and the corresponding L value, the neutron skin for zirconium, for ruthenium, and also for lead. You can see in this slide plot that the neutron skin for both ruthenium, zirconium, and lead have a good linear relation to the LC values. Here we have three values: 20, 47, and 70. So then we calculate the nuclear density and take it as input in our model study to discuss the final observables. The first sensitive observable.
Can you go to this extended?
Okay.
The term that they added is for what's the physics? What's the physics terms?
As far as I think it's the effective three-body interaction. Is it
body interaction? There were already some three-body interaction, right? The last term, for example. I mean, but what is this additional term? Like, what kind of physics are included here?
I think discuss with others is that they include more three-body interactions here.
It's the mean field. Here it's the kind of the mean field.
Yeah.
Approximation here, right? There.
Yeah, but I just want to know the three-body. There are many different ways.
So effectively.
Yeah, I think we use the effective density. Well, mean field. So it's not really a three-body interaction.
Yeah, but they must have some origin like momentum data. So okay. My question is, the people, if I understand, the PRX data, right? This large neutron skin. In the traditional DFT, if they use the symmetry energy, let's say 50 or 70 MeV, They will not be able to, yeah, they will still not able to, yeah, you show here, still far away from the P-REX data. Is this because you add these extra terms, which even keeping the same L, you can still describe it? I mean, would this will be very different from other approaches, right?
So you should compare the LC value here. The LC
Yeah.
value is 71.
Right.
So
But
So the
I'm
upper
saying
limit-
compared to the other DFT approaches, which does not have these extra terms, you will have some systematic
Is that right?
differences. I'm
Uh-huh.
asking you, I don't know.
I don't know either.
No, even with the extended actual terms, they still cannot get that even.
Okay, but go back to the previous slide. The one you showed, no, sorry, forward. When you show the, yeah, look, they actually are reaching the prediction is right on top, right, of the P-REX
yes,
for the lead.
It's 1 sigma.
Yeah.
No, not 1 sigma. The open black is sitting on top of the black. You actually are describing the P-REX data.
70 with 70.
No, but with this,
No,
L you normally get to, that's the typical. I don't think this is very different than with other.
But other people cannot, the P-REX data is always about their prediction. If I remember.
yes. When we doing this study, the results are not coming yet. So
It's 70, right? So it's
we use 70 instead of 71 from PREX.
Understand.
Right.
So-
Others don't use 70,
So
they use
from
smaller values.
so from PREX 2, they get 70 pretty much
I mean,
at the low C.
typical construction of SCARM is such that you cannot get large L values, you run out of L values. So most SCARM interactions, which are not weird, will end up around 80, 90, that will be it. And then you have some wacko ones that go 120 or something. It's an inherent in the
I see.
parameter.
So in the SCARM model, you cannot get large neutron scan no matter what you do at
Yes.
some point, right?
If you go to the relativistic formulations, usually you have the opposite. You get big, you cannot get small skins. So there is a gap actually, or somewhere where the P-REX lies, but it's a tied to the parameterization. And it's not clear how isospin comes here. This looks like some momentum dependence, I think. But there is a momentum dependence over the area.
You mean there's momentum dependence in the SHF?
This
In the
this
extended.
K looks like gradient momentum.
Yeah, the what's in the red box according to year 1 is momentum dependent term.
Like momentum dependent, density dependent, momentum dependent. The weakness of the normal curve is just the momentum dependence of the original is just quadratic. So you only change effective mass. But if the momentum depends, then it's more complicated. So maybe this accomplishes that.
Yeah, I assume this is trying to make it stiffer.
Thicker and in a more sophisticated manner, or realistic manner. But it's, I don't, there's no isospin here as it's written. Okay, so you could just go on.
So let me continue. So then we discussed some sensitive observable. Firstly, is the multiplicity distribution ratio, as I already introduced. So we found that the multiplicity distribution ratio between ruthenium, and zirconium, you'll see that in this plot. And if the L value is larger, the deviation from unity is larger at most central collisions. So to quantify these differences, we propose the observable, there's relative differences of the mean multiplicity between ruthenium, and zirconium at top 5% centrality. And then you can see that this R value have a very good linear relation to the neutron skin of isobars. And in this plot, each curve corresponding to the different model studies, and we use several models, the MPT, two versions, the default version and the stream mapping version, and also the URKMD, the hygiene. We also include the initial models like the Trento global to calculate the relation between R and the neutron skin of isobar. And you can see that all the trends are follow, all the results are follow the similar trend. And since we can get the R values from the data, we can use this method to extract the L values and also the neutron skin of isobars. So since the R is a relative measure, so it's much of the experimental effect and the systematic uncertainty are cancelled. So this is the first method we proposed. And the second method we proposed is mean PT ratios, and is similar to the multiplicity distribution ratios. Since if the two systems have the same total entropy or energy density, a smaller size will give a larger mean PT. So ruthenium should have a larger mean PT than the Collins collisions. So a very interesting thing for the mean PT is that we know the mean PT are affected by the bug property of the QGP medians. If you focus on the top panel of this plot, you will see that the mean PT for the Collins collisions do depend on the bug viscosity or the shear viscosity in the hydrodynamic simulations. But if you take the ratio between the two systems, you will see that this ratio are quite robust. It's independent of the is almost independent of the shear viscosity and the bug viscosity, which means they are independent of the detail of the QGP evolutions. So we will give a very good features to probe the nuclear structure in the initial state. So actually, we give plot the mean PT ratio and the transverse size of the collision areas. We found that the mean PT ratio is inversely proportional to the nuclear size ratio in most central collisions. And we know the mean PT ratio can be measured very precisely in heavy ion data, and we can also use this method to get the neutron skin and also the slope parameters of the symmetry energy.
But yeah, in this calculation, if I remember, you use a large nucleon width, right? I don't remember.
Yes,
like
yes.
one Fermi bigger than one Fermi, right?
This width is from the base analysis.
So it's a Jetscape. It's like 1.1.
Yeah.
But you know we also say if you use a very large width, you tend to reduce the mean PT ratio. In other words, the radial flow response is actually got a little bit diluted, and you can get a good agreement. But if you use the nucleon width, which is typically constrained by other observable, which prefer like 0.5, then this ratio will be much higher. I mean, that's a typical feature. If you use a smaller nucleon width, then this predicted the mean PT ratio.
You mean the nuclear width will have a very
big effect on this.
So the mean PT
the V2PT correlation prefer small width, and this actually prefer large width.
But the V2PT observable is a correlation of fluctuation observables.
Yeah,
the mean
sure.
PT is just the mean value. It's quite different.
But also, the trajectory, this study by Wilkie and Howard, when they also include the cross section, like constrain the total cross section of the heavy ion collision to match the experimental data, and they also prefer a small sigma, small width. That was shown last week. Right?
If I remember,
there are many observables which somewhat prefer small nucleon widths, and others prefer large widths, like this observable.
Yes. Thank you for the suggestion. Maybe we can say if there's some differences, we change the nuclear width in the mean PT calculation.
There's some computation between different observables. That's something that.
Yes. Thank you. So actually, we have already applied this method to the star data. So this is slide showing the star preliminary results on the multiplicity distribution ratio and the mean PT ratio to extract the L parameters. So the top panel showing the multiplicity distribution ratio and use the mean multiplicity difference is we can extract the L value, LC value here. The way we do it is that we calculate the mean multiplicity ratios at from the model with LC equal to 20, MEV 47 and 70, and we get 3 points. And then we use the experimental data to extract the L value corresponding to the experimental results. And also, in a similar way, we get the values from the mean PT observables. You can see that the two LC values are quite consistent with each other. Of course, if we use L instead of LC, we can also extract the L values related to this method. So now we can compare with, we can also compare with these L values with to the worldwide data. And in this paper, Professor Boani's very nice paper gave a very nice overview of the L value from the worldwide data. And we also put our values here, the 2 point from mean PT and mean multiplicity. And we found that our L values are quite consistent with worldwide data with good precision. And the large uncertainties are most come from the nuclear deformations. We also put the PERX2 data result here. The data is above than the worldwide data, but with large uncertainties. So as far
another question. So in this model, if you go back one slide, there's a question I always have is in one observable for the multiplicity ratio, you're comparing you basically extract everything from a global model.
Also gender.
Okay, I mean what you shown here is a global.
It's
model,
global,
right?
yes.
So the difference, the difference due to final state effect probably should be considered. But then the other thing is the DFT uncertainty. So this is all SCRM kind of density functional. I mean, according to what you just said, if you use a covariant DFT, you probably get a systematic change in the L value. I just wonder, would that be something one can check? Like if you get some density distribution from covariant density functional, and check the value extracted for the L, would that how much difference you will get?
I think the systematics is still about the same line, I would say.
Yeah, but there's a shift in the centroid, you said, according to what you said.
No. What I was saying is that parameterizations, by the nature of the parameterizations, the relativistic have hard time getting high L values, and relativistic have hard time getting small values, and non-relativistic high values. And there is a gap between the two.
Right. But you think
but as long as you bracket, maybe you shouldn't go it. If you bracket the value that you get, you go low and you get to go down.
but this is only checked using the SCRM.
Well, if you did it relativistic, you would get about 100 or something.
There's no way.
But about the same line, I would say, still.
Okay, so you will get a different L value.
You would
But
get different L values, but the correlation line would still be
That's
about
fine.
the same.
That's fine. But there basically there's model uncertainty which is still there.
At this point, it's maybe smaller than the experimental uncertainty.
But you said you will get a very large L if you use.
Now you have to modify, so you have extra terms to the relativistic one to get down. Just like in SCRM, you have 2 extra terms to go up. Yeah.
Is it possible to explain this afternoon, like how can this be done? I mean, I don't know if you because
I don't have relativistic one.
no, I mean just the idea.
Afanasiak, who was here last week, he does the relativistic.
Yeah, but we didn't discuss this topic.
So let me. So the way we use the initial model is to neglect the final state effect. That's because we assume that the one reason is that we assume that the initial total entropy and the final multiplicity have the very good linear relation, which means the final multiplicity proportional to the integral entropy, and the factor is same for the Rossini and the zirconium collisions. That's the one reason. And other reasons, if we can use some final model, final state, some model with some evolutions, that's good, but you know that's time consuming. So sometimes if we talk about multiplicity distribution, we always use the global model for the fitting or the Trenton model. Yeah. So that's maybe the reason. But if you can do some final state, some simulation with final state effect, that's good. But I think that's very time consuming. So
You probably won't change the ratio too much.
yeah, probably.
Values of the multiplicity would be quite different.
Yeah, but we didn't. We actually didn't do that kind of.
I think one thing one could check is that for different approaches, we also have Trenton model, right? Different approaches. If people start with the same set of parameter and then check whether you get the same answer. This was done for the deformations recently. In task force, we actually come up with this list of deformation.
We
didn't check it for the radius variation in detail. Yeah, it's just a comment.
We do some studies, but
Okay.
you know, the particle production from the viscosity is unknown for us. Yeah. So this may be.
What that means is that the people who running their own model, they could just check it because you probably cannot run the models.
So if we use MPT model, but the particle production, the multiplicity is fixed, so we have no effect on that. If we use the hydrodynamic simulations, the particle production depends on the viscosity. You know, the entropy is increased if we include the shear viscosity or bulk viscosity. So they have some uncertainties, and they also have some uncertainties in the theoretical to how to handle the particle production with the viscosity. Yeah.
There is no viscous particle production in MPT.
There is. That's why he said that he don't know how to fix it because
Yeah, that's the reason.
baseline is moving around when he put in viscosity.
But if some
Because then he needs to match
people
the
have some
data.
idea on that, that's very good things to do that.
Yeah, so that probably means when you change the shear viscosity, if you want to fix your multiplicity, but keep it unchanged, you probably need to modify something else.
Yes, that's correct.
Yeah, I think we can continue.
Okay.
Let's continue.
So so far I have introduced two methods. Actually, these two methods are not really isospin sensitive, and it's really because we know the charge densities. So we measure the mass density differences, so we extract the neutron skin. And in heavy ion collisions, we also have some observables, which is also isospin sensitive. So this method is called a net charge ratio, net charge. So in very peripheral collisions, and the idea is very simple. So for the collision of nuclei with large neutron skin thickness, we will have more neutron collisions at most peripheral collisions. We will create less participant charges and thus less final state net charges. So if we look at the net charge ratios between Rossini and zirconium from the URKMD simulation, you will find that the ratios will become larger at very lower multiplicity range. And this is the neutron skin effect. And actually, the net charge ratios can be written in this formula under the superimposition assumptions. And these formulas depend on two quantities. One is the Q, which is the fraction of protons among participants' nucleus. And this plot shows the calculation of the Q from the Trenton simulations. You can see that the Q is larger for ruthenium than zirconium, and the different L value give very different prediction of the Q trend as function of multiplicity. And another variables in this formula is the alpha value. The alpha value is very interesting. The alpha value is the net charge ratios in neutron to proton interactions. And from all the model, we have known the PCR, the hygiene, the URKMD, we get the alpha value is minus 0.35 around that. But if we look at the recent star preliminary data on the net charge ratio, we can extract the alpha value around 0. And this is what we do not understand yet. And maybe some new physics behind it. So they also have some other observables is also spin sensitive. For example, the spectacular neutrons, and the idea is quite similar to the net charge. So the spectacular neutrons in ultra-central collision are corresponding to the net charge in the ultra-peripheral collisions. So of course, the yield of the ratio of the free spectacular neutrons is also a clear purpose of the neutron skin thickness proposed by this also including Jia Yong and his collaborator.
So
And
the
sorry.
alpha values?
Yes, this is for isobars. They compare
the
them.
value of alpha.
Oh, sorry.
Yeah.
Yeah. Okay.
So how do I? Oh, so all these three lines are produced with alpha equals to 0, right?
Yes, we vary in the L value.
So
Yeah.
what the results look like if you put in alpha equals to minus?
Here, this plot showing the alpha value is minus 0.4.
So compared to, oh, okay.
It's quite large. It's huge.
Oh, I see. So about 1.5 as compared to 1.2,
1.3, something like that.
The points are different.
Yeah.
Okay.
So in my talk, I focus on the nuclear neutron skin determinations. Actually, in isobars, you will hear from a very nice talk from Jiang Yong that the nuclear deformation is also different in isobar. The V2 ratios above 1 indicate that the ruthenium have a larger critical deformation. The V3 ratio below than 1 indicates that the zirconium have a larger outcrop deformations. So they have size differences between isobars. Actually, we also proposed some observables. For example, the 3-point asymmetry cumulant, which is also sensitive to the deformation for both beta 2 and beta 3. Okay, let's go to my summary. So the star isobar data indicates that the zirconium have a single hero type neutron skin and consistent with the DFT calculations. And this may be very crucial for our understanding of the CME baseline in isobar studies. And also I propose several methods with precision isobar data can use to probe the neutron skin thickness and symmetry energy. The observables include the multiplicity distribution ratio, mean PT ratio, net charge ratio, and also the spectator proton ratio proposed by Jiang Yong and his collaborators. So this is my talk. Thank you.